Hi, I'm John, and I'm here today to talk about how it is we can record and measure earthquakes. Now, earthquakes generate seismic waves, and those seismic waves can go, for the larger earthquakes, all the way around the Earth. But as humans, we really don't feel those earthquakes very often. For example, in California and in Alaska, where earthquakes are happening every day, you still don't feel the earthquakes very often. So it turns out humans aren't that good at recording or feeling earthquakes. And what I'd like to do first is show you an example of an earthquake that was very, very big, caused damage, and was heavily felt by a lot of people nearby, but sent waves all the way around the Earth, and only the seismometers were able to see that earthquake. Here's a slide that shows the recordings from an earthquake that happened in Japan in 2011. And you probably remember this earthquake. This is a magnitude 9 earthquake that caused a huge tsunami. Many, many people died, and also caused damage to a nuclear power plant. This slide is showing recordings from the Japan earthquake from multiple seismometers around the Earth. The x-axis is time, which runs out to about 6 hours after the earthquake. The y-axis is distance, and the distance here is measured in degrees from 0, which is the location of the earthquake, to 180 degrees, which is the far side of the Earth. We're going to simplify the figure a little bit because it's rather complicated by just looking at a few stations and just the surface wave arrivals. We can watch the surface wave, which is actually the largest amplitude wave that you get after an earthquake, and which after the earthquake travels away from the epicenter in all directions. The waves are recorded as they arrive at the stations, nearest stations seeing the waves first, and as the distance increases, the time it takes for the wave to arrive increases. Once the waves reach 180 degrees, which is the opposite side of the Earth, they cross and begin to travel back towards the epicenter. Stations record another arrival as the wave passes each station again. The original graphic shows this pattern recorded on many stations at many different distances. Each line is from one seismometer, but the pattern is the same as the wave travels away from the epicenter. Each seismometer records it as it passes with a second arrival as the wave continues around the Earth and passes the station again, traveling in the opposite direction. After about 3 hours, the surface waves have traveled all the way around the Earth. Now, what I'd like you to do is look at the slide and look at the scale. In the bottom right corner, you'll see there's a scale that says 1 centimeter. That's 1 centimeter of ground motion. That's the ground moving up and down 1 centimeter. And what you've realized, if you look at it, you'll see that, in fact, everywhere in the Earth moved up and down at least 1 centimeter. Now, if you can imagine trying to move this building, or whatever building you're in, a whole centimeter up and down quickly, that would really be a very, very big shake. But no one on our side, or our part of the world, felt the earthquake because it moved up and down very, very, very slowly, because the waves are really long waves, like a really, really long ocean wave. And so everything moved up 1 centimeter and moved back down 1 centimeter. So people couldn't feel it, but the seismometers were able to record it. And so that shows why really we need to come up with a seismometer to record our seismic waves, so that we're able to analyze the waves and help figure out what happened during the earthquake, and also how the waves can tell us about the structure of the Earth. So what I'd like you to do then is to build your very own seismometer. And what I'd like you to do is use materials that you can find around the house or around your classroom. So maybe your seismometer might be made partially of paper plates. You may have a few of those around. Maybe you've got some springs that you can use. They can be helpful for a seismometer. Maybe you just need some string, some wire. You need to have maybe like around here at work, we've got just some coffee stirrers. Maybe you can use rulers, tape, and then you might need some way. You probably need some way to record what's happened. So maybe you might need pens and paper somehow as part of your recording system. So if you look on the list on the slide, then you'll see that there's also, might have sinkers from fishing lines, maybe paper towel rolls, straws, marbles even, pipe cleaners, and maybe some wire. So what the idea is in your case, to find some things around your house or your classroom that you can use. And then when you do it with your students, you want to give them maybe a table of a variety of items that they can choose from. And then you also ask the students to bring something, maybe one or two things from home that they think they could make as part of their seismometer, because that would help them to really be creative in building their seismometer. Now, if you're going to build something, you need to have a design criteria. So here's the design criteria that I'd like you to use. First of all, as we've already talked about, you need to make it out of something that's fairly inexpensive, just materials around the house or the classroom. Then you want to be able to record relative sizes of shaking. So it's got to be able to not just shake, but also record the differences. It needs to be able to record it for up to a minute, so it needs to be able to keep going, not just have one instantaneous recording. If it's a really good design, it'll be able to record the time differences between the arrivals in some way. And then if it's a really good design, you'll be able to record shaking from the table moving, from someone jumping on the floor, and maybe even from throwing a ball or some object against the wall or against the floor. So once you've done that, then you can maybe think about what your design is going to be, maybe draw a picture, build your design, and then from there, once you've built your design, then document your design and write down why you used the components you used, what the different parts of your seismometer are, what the reasoning behind the different parts of your seismometer. And once you've done that, then we can come back and I'll show you the design that I made, and we'll talk about how a seismometer works and what we really need to have in a seismometer to be effective.